Imagine for a moment that you are standing absolutely still. The air does not stir. Your heart marks the seconds with metronomic certainty. Somewhere beyond the window, the sun rides across a sky that appears to pivot around a motionless Earth. This quiet picture, space as an invisible stage, time as an invisible clock, was the common-sense cosmos bequeathed to us by Isaac Newton. It feels correct because our bodies evolved at the scale of meadows and mountains, where distances are measured in footsteps and durations in heartbeats. Newton declared that space persists forever as an unchangeable emptiness, and that time flows forward everywhere at the same regal pace, whether you are in London, on Mars, or alone between the galaxies. The universe was a box, and the box was always the same size. The only things that moved or aged were the trinkets placed inside. For 2 centuries, this vision stood unchallenged, a marble pillar of certainty. Then, in the spring of 1887, 2 men in Cleveland set a slab of stone floating on Mercury and sent a beam of light splitting in 2. Albert Michelson and Edward Morley wanted to feel the motion of Earth through the Newtonian void by measuring how light was carried along like a leaf on an invisible river. To their astonishment, the light refused to oblige. The halves of the beam arrived in perfect step, as if Earth were motionless, as if there were no river at all. A smaller, more cautious experiment might have been dismissed as faulty wiring. But the result returned, again and again, across seasons and instruments, until the pillar itself began to fracture. If there was an absolute space against which motion could be judged, it was hiding its presence with uncanny perfection. The dilemma spread through physics like a hairline crack. Other puzzles gathered. The way magnets and charges seemed to whisper to each other across the vacuum, the way certain radioactive clocks kept their own capricious beat. Nature appeared to be protecting something, guarding a consistency that Newton's separate space and time could not articulate. No one knew yet that the secret required uniting 2 words that had never before shared a syllable: space, time. Enter a young patent clerk in Bern, 26 years old, armed with a fountain pen and the stubborn habit of riding streetcars while staring at receding clock towers. Albert Einstein did not yearn to overthrow Newton. He wished only to understand what Maxwell's equations on electromagnetism were murmuring about the speed of light. Those equations offered no seatbelts. The speed was fixed, the same for every observer, everywhere, always. To preserve that single, stark fact, the tidy compartments of absolute space and absolute time had to be surrendered. What replaced them was a single, pliable fabric, whose threads are intervals measured not in meters or seconds alone, but in a marriage of the 2. Einstein called the marriage spacetime. Picture 2 friends bidding farewell on a railway platform. One boards a train that glides away at a steady speed. The other remains beneath the iron canopy. They compare watches, not by looking at each other, but by sending light signals along the tracks. When the traveler returns at journey's end, her accumulated minutes do not match the minutes of the one who stayed. Neither watch is broken. Each faithfully recorded the length of its own path through spacetime. The geometry of those paths differs, much as the distances traced by 2 hikers differ if one climbs switchbacks while the other cuts straight across the valley. We are forever hiking through a 4-dimensional wilderness, but because our eyes see only 3 dimensions at once, the curvature of our itineraries is hidden from view, revealed only in the mismatch of the dials. Thus the old absolute stage evaporates. Space cannot hold still, for no universal clock declares what still means. Time cannot march in universal cadence, for every heartbeat charts its own contour across the landscape. The only absolute is the speed of light, a cosmic speed limit enforced not by decree, but by the very shape of the arena in which we move. To speak of space without time is now akin to speaking of melody without duration. To speak of time without space is to sing of a story that never began. Yet this is only the first peel of the onion. Special relativity, the 1905 theory that delivered spacetime to the world, was limited to observers who glide without jostling, who feel no push or pull beneath their feet. It said nothing of gravity, the ancient mystery that had guided planets long before Michelson, Morley, or Einstein. But the success of unifying space and time was too profound to ignore. If light's refusal to pick a favorite speed revealed spacetime, perhaps weight, the tug on a stone, would reveal something more. That the fabric itself can curve, can sag under mass, can guide the stone not by force but by geometry. We stand at the threshold of that deeper country, where falling apples and orbiting worlds are no longer pulled, but simply follow the folds of a four-dimensional quilt. For now, pause on the platform where we began. Feel the boards beneath your shoes, the pulse in your wrist, the hush that follows the departure of the train. Newton's box is gone. The night is no longer a fixed vault, and tomorrow is no longer a universal certainty. Yet the exchange is not loss, it is translation. What seemed rigid has become flexible. What seemed separate has become inseparable. We are left with a continuum, quietly humming beneath every event, asking only that we reconsider what it means to be here and what it means to be now. Imagine for a moment that you are standing perfectly still. The air around you seems motionless, the ground beneath your feet solid and unmoving. Yet in truth, you are already traveling. The planet beneath you spins, it orbits the sun. The sun itself drifts through the galaxy, and the galaxy rushes outward with the expanding universe. What feels like stillness is, in reality, a vast and complex motion through something we once thought separate, space and time. But they are not separate. They never were. They are threads of the same fabric, woven so tightly that to pull one is to tug the other. This is the quiet revelation that waited beneath Newton's laws, hidden in plain sight until a young clerk named Albert Einstein dared to ask, what if the universe is not staged within space and time but is made of them? To see how radical this idea is, we must first let go of the obvious. We are taught to trust our senses. A second is a second, a meter is a meter. They feel fixed like the stage upon which the drama of the cosmos unfolds. But the universe does not obey our senses. It obeys something deeper, geometry. Picture two travelers. One remains on Earth. The other boards a ship that accelerates to within a hair's breadth of light speed, toward a distant star, and returns. When the voyager steps back onto the home world, the reunion is bittersweet. The traveler has aged perhaps a year. The one who stayed behind has lived decades. Both carried accurate clocks, both counted heartbeats. Both are right. Time itself has flowed differently for each. There is no hidden mechanism, no mechanical fault. The interval between departure and return, measured not in seconds but in the marriage of seconds and kilometers, has been the same for both. We merely sliced it differently. This is Minkowski spacetime, a four-dimensional arena where every event, your next breath, the birth of a star, the last glimpse of a dying rover on Mars, has an address not in space or in time but in their union. To travel through one is to travel through the other. Speed is merely the angle at which you tilt your path. Move faster through space and without choice, you tilt away from the time axis of someone who stays behind. The Lorentz transformations, once seen as forbidding equations, become gentle rotations of perspective, like turning your head to view a sculpture. The statue does not change. Your view does, so it is with spacetime. No observer owns the true perspective. Each carries a local truth and the laws of physics honor everyone. But how do we measure anything in such a shifting country? We need a ruler that does not stretch or shrink, a clock immune to the moods of motion. Nature gives us one, the speed of light. It is the only speed that every traveler, no matter how fast or slow, will agree upon. Nothing can overtake it. Nothing needs to. It is the invariant against which all else is gauged. From this quiet constancy emerges the spacetime interval, a marriage of distance and duration that remains the same for every traveler everywhere. It is the true measure of separation between events. Space or time alone may warp, but their combination stands unbroken. Imagine two stars that explode simultaneously in some faraway galaxy. One flash races toward Earth from the left, the other from the right. Because the galaxy is moving, we on Earth see one explosion arrive a century before the other. Yet the spacetime interval between the two blasts is unchanged. It is a beacon fixed in the storm, a granite obelisk amid shifting dunes. From this constancy arises structure, the light cone. At every moment wherever you are, an invisible cone opens around you. Its surface is traced by light paths. Inside the cone lie all events that could, in principle, receive your influence. Outside, they are forever beyond reach. The cone is personal, redrawn at every step. Yet it is also cosmic because the causal architecture of the universe is built from countless overlapping cones, a froth of possibilities and prohibitions. To glimpse a light cone is to glimpse the silhouette of fate. These ideas are not curiosities for starships. They live beneath your feet. The GPS in your phone relies on clocks that tick faster in orbit than on Earth's surface. Engineers must correct for the tilt in spacetime caused by both speed and gravity. Without those corrections, navigation would drift by kilometers each day. You trust the map because unseen mathematicians quietly account for the elasticity of time itself. Still, the geometry of relativity is more than utility. It is a mirror held up to existence. We once believed the universe was a grand clockwork, ticking uniformly from past to future. Now we see it as a vast, flexible tapestry. The threads are events. The weave is spacetime. Pull it taut near mass and energy and time dilates. Ripple it with colliding black holes and distance itself oscillates. The tapestry does not merely hold matter, it responds, breathes, remembers. And here, at the edge of understanding, questions begin to glimmer. If spacetime can bend, can it tear? If it tears, what lies beneath? Some physicists whisper of a deeper fabric, quantum threads from which even geometry is woven. Others speak of holograms, of dimensions curled too small to see. We do not yet know. What we do know is that the smooth continuum Einstein gave us is not the end of the story. It is a chapter heading. So we stand, quiet observers on a twirling world, learning to feel the weave. Each heartbeat is a stitch. Each footstep a tilt in the cone of the possible. We are not passengers upon spacetime. We are features of it, little eddies in a river that rushes not through space, not through time, but through something larger and older than either. Tomorrow, we will follow the ripples farther to places where the river foams and churns, where clocks stop and distances dissolve. Tonight, let the stillness speak. Feel the earth carry you through the dark. Sense the gentle tug of the future cone opening ahead, the fading echo of the past cone closing behind. You are already moving. You were never otherwise. Imagine you are standing in a small, windowless room. A ball you release does not hover, it falls. If the room were on Earth, you would say gravity pulls it. But what if the room were out in interstellar darkness, no planet in sight, yet accelerating upward like an elevator on invisible cables? The ball would still strike the floor, and you would still feel your own weight pressing into your soles. Inside the sealed room, no experiment you can perform, dropping objects, swinging pendulums, pouring tea, will distinguish the tug of a planet from the push of an accelerating frame. This indifference is the equivalence principle, the quiet hinge upon which Einstein turned all physics. It says that the sensation we name gravity can be replaced, moment by moment, with the geometry of motion. Weight becomes a local illusion. What persists is the shape of space and time themselves. To see how radical this is, recall the sky of Newton. There, gravity was a force mysterious and instant, leaping across the void to clasp moon to earth, earth to sun, sun to the distant Uit clouds. It worked, but it worked like an edict delivered faster than light, with no messenger anyone could name. Einstein, disturbed by this ghostly immediacy, asked a childlike question. What if the moon is simply following the straightest path it can find, but in a realm that is already curved? Picture spacetime as a vast, elastic silence. Where no mass intrudes, it lies flat. Light and matter sail across it in simple, unbending lines. Bring in the sun and the silence dimples. The lines that once marched forward now tilt, gently at first, then steeply, funneling everything inward. Planets orbit not because they are lashed by cords of force, but because they are gliding on the tilted surface, the way a coin rolled along a bowl's rim circles until it settles. This gliding is geodesic motion, the nearest thing to straight that curved reality allows. Mass energy tells spacetime how to curve. Curved spacetime tells mass energy how to move. The sentence is short, symmetrical, and complete, yet within it lives the architecture of galaxies. A star's worth of hydrogen, burning quietly, presses outward with light and heat. Its own gravity answers by shaping the surrounding spacetime into a well. The balance of these whispers holds the star steady for 10 billion years. When the fuel wanes, the well deepens faster than the star can adapt, and the outcome, white dwarf, neutron star, or black hole, depends on how steeply spacetime can curve before the universe forbids further collapse. To us, accustomed to force and counterforce, this exchange feels alien. We grow up pulling ropes, pushing swings, feeling muscles contract against weight. But across the solar system, no muscles steer the planets. They simply fall endlessly around the curvature their own presence helps create. The fall is silent, the path exact. A millimeter's deviation in the shape of spacetime near Earth would, within months, nudge satellites into new altitudes. Global positioning must recalculate each nanosecond, correcting for the fact that clocks aboard those satellites tick faster than the ones in our phones. Gravity stretches time itself. Einstein distilled these insights into 10 coupled equations, each side balancing geometry against content. On the left, the curvature of spacetime; on the right, the density and flow of mass energy. The equations do not shout, they murmur. Yet their whisper predicts that space can undulate, carrying ripples at light speed across black deserts. A billion years later, those ripples raise and lower the distance between two mirrors on Earth by 1,000th of a proton's width, and we hear them as chirps in laser light. The first such note arrived in 2015, confirming what microphones of glass and vacuum had been waiting for. Earlier hints had already conspired in Einstein's favor. In 1919, during a total eclipse, starlight was seen to bend around the sun by the precise degree his geometry demanded. News traveled slowly then. Telegrams carried the result across oceans, and the name Einstein passed from academic journals into household myth. Yet even before the flashbulbs, Mercury had betrayed Newton. Its elliptical track around the sun swings like a slow compass needle, 43 arcseconds per century faster than any known mass could explain. The discrepancy was tiny, no wider than a dime viewed from a mile, but it had haunted astronomers for decades. When Einstein computed the same excess using the curvature produced by the sun, the number matched exactly, and he later said that his heart had truly trembled. Still, the equations give no picture of how curvature propagates. They speak in tensors, not textures. Imagine the surface of a lake. Equations can describe every ripple, yet they do not tell us what water feels like between fingers. Similarly, we do not yet know what spacetime is made of, only how it responds. Is it a continuum, smoothed down to the smallest conceivable scale? Or does it grain into quantum foam, where geometry itself flickers between possibilities? The question remains open, like a door at the end of a long corridor. For now, we live on the gentle slope of Earth's well. Each heartbeat, each sunrise, is a low note in the curvature produced by 5 quadrillion tons of rock and iron. We climb mountains and feel heavier in spirit if not in scale. We age microseconds less at altitude than at sea. These are not metaphors. They are the measured drift of time in a dented cosmos. Consider 2 astronauts floating side by side above the planet, gloved hands almost touching. If they drift a few meters nearer, the curvature beneath them differs imperceptibly, yet enough that, left alone for long enough, their paths would separate. To stay together, they must reach out, not because a force pulls them apart, but because space itself tilts them into separate futures. The gesture looks like affection. It is also geometry. And so we arrive at a strange humility. Gravity is no longer a monarch issuing commands. It is a stage built of silence, its planks bent by every actor who walks across. The actors, galaxies, stars, oceans, thoughts, cannot exist without the stage, yet the stage is meaningless without the actors to bend it. We are both subject and substance, the singers and the song. Out beyond Neptune, the dimple of the sun flattens into a shallow wake. Voyager 1 glides there, still receding, its tiny plutonium heart beating against the hush. It follows the straightest line available, yet that line is curved by the mass of a star it will never again approach. In 1 billion years, when the sun has shed its outer layers and cooled to ember, the craft will still be falling along the ancient slope, a silver memory of a species that once understood, however briefly, that falling and orbiting are merely different names for following the shape of time. We do not see this curvature directly. We feel it as weight, as the arc of a tossed ball, as the inevitability of meeting the ground. But the ground itself is ground only because it resists the curvature pressing down. Remove the planet, and the same atoms would scatter into the void, rearranging the shape of spacetime as they go. There is no fixed floor beneath the universe, only an endless negotiation between what exists and where it can exist. Perhaps the most haunting consequence is that time, too, is part of the fabric. A second near a black hole passes as peacefully for the infalling traveler as any second here. Yet when they look back, they see the outside universe blue shift and accelerate, stars whirling into galaxies, civilizations blooming and fading in flickers. Curvature allows 2 hearts to beat at different rhythms while each feels perfectly normal. The universe is not cruel, it is impartial. We are left with a spacious uncertainty. If mass and energy shape spacetime and spacetime guides motion, what is spacetime when neither mass nor energy remain? Empty flatness or something alive with quantum possibility? And if curvature can become so steep that light itself cannot climb out, might there be regions where space and time swap roles? Where forward is no longer a direction you choose but one imposed by the geometry of horizons? These questions do not spoil the picture, they enlarge it. Every reliable map has edges labeled "Here be dragons." Einstein's dragons are not monsters of superstition, but labyrinths of mathematics we have not yet learned to read. To enter them, we may need new languages, languages that speak of entanglement and geometry in the same breath, that treat information as substantial as stone. For tonight, step outside and look at the sky. Between you and the stars lies a planet pressing gently upward, a curvature so slight that birds defy it with lifted wings. Yet that same curvature steers the moon in its monthly spiral, binds the fires of distant galaxies into the slow dance of clusters. Feel the tug in your souls. It is not a force reaching through space. It is space itself tilting you toward the center of Earth, a fall so perfectly balanced it feels like standing still. Somewhere beyond the reach of our instruments, the last echo of the Big Bang still ripples, stretched into wavelengths larger than galaxy clusters. Those primordial waves are curvature incarnate, memories of the instant when all that would ever be was compressed into a single, quivering moment. If we could hear them, we might recognize the same tone that keeps our feet on the ground, the same hush that guides Voyager into the dark. We live, then, inside a single, breathing shape, guests of a geometry we did not choose but help create. Tomorrow, the equations will still balance. Tomorrow, the questions will still outnumber the answers. Tonight, the stars wheel overhead, following paths that are straight in their own sky, curved in ours. Imagine you could peel the earth away from beneath your feet, roll it between your palms until every mountain and ocean became a smooth, dark marble. Then keep pressing. Press until atoms buckle, until nuclei kiss, until the marble shrinks to a pinprick yet keeps the full 8,000-mile heartbeat of its gravity. That pinprick is not fantasy. It is the Schwarzschild solution, the first exact answer Einstein's equations whispered to Carl Schwarzschild in the trenches of 1916. If enough mass is crushed inside a small enough shell, spacetime folds in on itself and never unfolds again. From a distance, the disturbance is oddly modest. A star vanishes, a darker star remains, circled by those still luminous. But step closer carefully, and the shape of space begins to tilt. Paths that once wandered freely now slide inward as if the ground itself has become a gentle, irresistible slope. At a certain boundary, the slope steepens to vertical. Beyond that, no future leads outward. This boundary is the event horizon, a surface of no return, not a wall but a horizon in time rather than space. Cross it, and the fastest signal you can send arrives, not at any distant friend, but inevitably at the center. The horizon is where light, trying to escape, hangs motionless in its own eternity, a frozen beacon no one outside will ever see completed. Inside, the folding continues. All roads converge on a point of infinite curvature. The singularity. The word is honest. Mathematics breaks there, and so physics suspects would reality itself. Yet we need not reach that abyss to feel the black hole's power. A human body falling through the horizon of a stellar mass hole would be stretched head to toe by tides before ever arriving. Imagine dangling above the Grand Canyon by a thread that inexplicably shortens. Your feet accelerate away from your head until joints part, then molecules, then atoms. The whole distorts space faster than any material can answer, turning flesh into a ribbon of plasma glowing X-ray bright. Time, too, is bent. Hover just outside the horizon with engines thrusting against the inward slide, and your heartbeat slows relative to every distant clock. A year of your life might match a millennium on Earth. Watch civilizations rise and fall between one breath and the next. But the slowing is not illusion, it is geometry. Gravity is the curvature of time as much as space, and near a black hole time tilts so steeply that merely holding position demands acceleration near light itself. No crew, no circuitry, no stone can resist the gradient forever. Eventually, everything slips. We have never stroked such a surface with human hands, yet we have heard it quiver. In 2015, two spiraling black holes, each heavier than 30 suns, drew together across 1 billion light-years. In the final instant, their horizons touched, whirling space into a storm of ripples. LIGO's lasers, 4-kilometer arms in Louisiana and Washington, felt the distortion. A shiver smaller than the nucleus of an atom, ringing like a bell at a frequency we could play on a piano. The note lasted 1/5 of a second, but carried the mass of 3 suns converted into pure sound in the key of C. We did not see the merger. We heard the spacetime drum. 4 years later, the Event Horizon Telescope stitched together nights of data from observatories on 4 continents, turning the planet itself into a dish the width of Earth. In the heart of the galaxy M87, they resolved a glowing ring, brighter than all the stars of the Milky Way combined. yet darker at the center than any camera had captured. The ring is not the whole, only the last light that can still orbit. Its diameter is what Schwarzschild predicted for 6.5 billion suns, and its lopsided brightness betrays the spin of spacetime being dragged like honey around a spoon. We have mapped the shadow, the thing that casts it remains hidden. Still, the questions outrun the answers. What becomes of information, the subtle pattern that once told whether a particle was here or there, once it slides past the horizon? Does it re-emerge in the faint glow of Hawking radiation, encrypted beyond recognition? Or does the universe keep a second set of books somewhere we have yet to look? Inside the singularity, does time end, or does it bounce, birthing new regions unreachable from ours? We speak of a point of infinite density, but infinity is a confession that we have reached the edge of the map. Perhaps black holes are less objects than thresholds, passages through which the continuity of spacetime is quietly knotted and cut. They remind us that emptiness is never empty. Even the calmest interstellar vacuum vibrates with the same curvature that can, given enough mass, become a cage. They teach us that gravity is not a force reaching across space, but the shape of space itself, and that shape can be sculpted into forms more extreme than any planet or star. Tonight, wherever you stand, a few of these silent marbles are drifting above your head, orbiting the galactic center like moths around a flame. They are the remnants of dead suns, the architects of future galaxies, the crucibles where elements we have never measured might be forged. They are also mirrors. In their gravitational lensing, we see starlight bent into rings, ghost images of objects behind them, the sky folded like origami. By such distortions, we weigh what we cannot see, charting the dark scaffolding upon which visible matter hangs its lights. To live in a universe that contains black holes is to accept that certainty has boundaries. We can predict the instant when a clock near the horizon will appear frozen to our eyes, yet we cannot say what the falling clock itself experiences at the singularity. We can calculate the last stable orbit, but not the fate of the information encoded in the infalling astronaut's smile. The equations give us everything up to the edge, then fall silent. And so the quiet returns. Somewhere a star exhausts its fuel, collapses, and briefly outshines its entire galaxy in a farewell burst of light. In the afterglow, space is left stitched with a new horizon, a stitch so tight it can never be unpicked. We continue to orbit, you and I, riding the gentle curvature of Earth, itself a mere ripple compared with the folds we have glimpsed. But the knowledge remains. Beneath the calm of every moment lies the possibility of deeper folds, of times and places where even the steadfast compass of light loses its way. Perhaps the next horizon is not far. Perhaps it waits in the still unexplained quickening of distant stars, or in the hush between heartbeats when gravity feels suddenly heavier. We walk upon a fabric that can strain until it tears, and through the tear, something, maybe everything, continues. What that continuation might be, and whether any thread of awareness can survive the plunge, is the darkness we have yet to illuminate. Imagine for a moment the sky at night. The hush of darkness, the slow turning of stars above a quiet field. We feel the earth beneath us as solid, fixed, the reliable stage on which our lives unfold. Yet this impression is a kindness granted by our smallness. The ground under your feet, the air in your lungs, the iron in your blood, all of it drifts within a deeper hush. The hush of space itself, quietly swelling like a tide that never reverses. Nothing you see betrays the motion. Galaxies do not scream as they glide apart. They exhale. Their starlight reaches us after journeys so long that the departure point no longer exists. Between the moment a photon leaves a distant galaxy and the moment it lands on the back of your eye, the universe has grown. Not the objects, but the emptiness they inhabit. The canvas has been stretched and the pigment of the cosmos has thinned, cooled, reddened. We are latecomers to a story already most of its way told, yet the telling is still underway, and we have only just learned how to listen. Once the word universe meant everything that is. Now it means everything that becomes. In Einstein's equations, spacetime is not a rigid box. It is a supple fabric that can be bent, dented, and, most startling, pulled outward from within. To accommodate this insight, cosmologists fashioned a model as simple as a sigh. A universe smooth enough that no place is special, yet dynamic enough that every place is in motion. They called it the FLRW metric, after the four minds who distilled it from the mathematics of general relativity. The letters themselves are dry ink, yet they sing of a cosmos breathing. Picture a translucent balloon dotted with ink. Blow gently. The spots separate, each one drifting farther from every other, not because they crawl across the rubber, but because the rubber grows. Galaxies are the ink, spacetime is the rubber. There is no center to the expansion. Every point sees itself as the unmoving heart of the drift. This is the Hubble flow, named for Edwin Hubble, who first noticed that the farther a galaxy, the faster it recedes. He measured the retreat with the only yardstick light allows, color. Starlight stretched toward the red end of the spectrum tells us the very wavelength is being elongated as it travels, a slow accordion note sinking ever deeper. If you could hear light, the sky would be a lullaby descending into bass. The same lullaby plays in every direction because the expansion is uniform. We do not occupy a privileged balcony. We sit in the orchestra with everyone else, listening to the pitch drop. Stretch anything long enough and it cools. Stretch a furnace and it becomes a refrigerator. The cosmos began white-hot and has cooled for 13,800,000,000 years. We still bathe in the afterglow, now chilled to a mere 3 degrees above absolute zero. Radio telescopes intercept it as a faint static coming from every point of the sky, snow on an old television that has never been unplugged. This is the cosmic microwave background, the oldest light we will ever see. It arrived when the universe was 380,000 years old, a tender age compared with its present adulthood. Before that moment, space was an opaque plasma, a fog of particles too crowded to let light pass. Then the fog lifted and light escaped, carrying a snapshot of the infant cosmos. Study the photograph carefully and you find tiny ripples, deviations of 1 part in 100,000. From such gentle creases would arise the great folds of galaxies, clusters, and voids we inhabit today. The wrinkles are seeds. Expansion is the wind that scattered them. To speak of size, cosmologists invoke a scale factor, a single number that grows with the universe. Set it equal to 1 today, and it shrinks towards 0 as we rewind the tape. At 1/10 its present value, galaxies overlap like fish in a shallow pond. At 1/100th, atoms break into nuclei and free electrons. At 1/10,000th, nuclei themselves dissolve into protons and neutrons. Keep shrinking, and the story reaches a moment when space itself is packed so tight that time begins to stutter. We call that beginning the Big Bang, though no explosion occurred in pre-existing space. Instead, space unfurled, carrying energy with it like a tide lifting all boats from nothing we yet comprehend. Run the tape forward again and the scale factor keeps climbing. For a long while, everyone assumed the climb must decelerate, gravity acting as cosmic brake pads. Then, in the waning years of the 20th century, 2 teams of astronomers trained their sights on distant supernovae, candles so reliably bright they can be seen across billions of light years. The candles turned out dimmer than expected, not because they were feeble, but because they sat farther away than a merely coasting universe would allow. Something was stepping on the accelerator. The unknown agent is called dark energy, a name that confesses our ignorance while acknowledging its effect. A pressure embedded in empty space, a tension that repels itself. It reveals its presence only on the grandest scales, where gravity's grip loosens. Nearby, it is imperceptible. Across the void, it gathers strength, bending the trajectory of whole galaxy clusters. Today, it accounts for 70% of everything, yet remains a whisper in the equations, a Greek letter we write and cannot yet read aloud. Because of dark energy, the expansion is not merely continuing, it is speeding up. Galaxies will accelerate away until, in 100 billion years, a future astronomer born in the Milky Way will see only darkness beyond our local group. The rest of the universe will have slipped over the horizon, redshifted into silence. That observer will inherit the same equations we possess, but far fewer clues. They may never know the cosmos had a beginning. We happen to live in the narrow window when the past is still visible, when the story can still be read in the fading embers of the Big Bang. What then is the age of all this becoming? Measure the Hubble constant, how fast space stretches today, and invert it. The number you obtain is a rough heartbeat of cosmic time, 14 billion years, give or take a few hundred million. Refine the calculation by folding in the way expansion has changed gear, first slowed by matter, later hastened by dark energy, and the answer sharpens to 13.8. A blink compared with the trillions of year stars will eventually shine, yet long enough for hydrogen to learn consciousness, for matter to look back at the darkness and name it. Stand outside on a clear night and you can feel the scale of the quiet. The stars do not shout, they hover, patient, like lanterns lowered into a well. Between you and them lies space doing what it has always done, stretching, cooling, carrying the light toward you even as it thins the light to red. You are not outside the process. The calcium in your bones was forged in stars that blew apart before the sun ignited. The water in your blood was once interstellar ice. Even the neurons that wonder about the sky are woven from threads spun in the first minutes of cosmic time. To study expansion is to feel the ground breathe beneath the illusion of solidity. Still, questions remain like soft afterimages when you close your eyes. Why does dark energy have the strength it does, neither overwhelming nor negligible, but poised to dominate only recently? Will it persist or could it decay, perhaps metamorphose into something stranger? Does the expansion pull space apart faster than black holes can swallow it, faster than galaxies can form, faster than thought itself can track? We do not know. We stand on the shore of an ocean whose other shore may not exist, watching waves recede into a darkness that deepens even as we name it. Yet the not knowing is not failure. It is the native climate of science, the same climate that once allowed minds to imagine that the Earth orbited the sun, that continents drift, that time runs slow in the presence of mass. Each generation inherits a larger sky, a longer past, a more tenuous future. Our gift to the next is to leave the questions a little clearer, the darkness mapped by one more candle. Somewhere ahead, perhaps, waits a moment when the scale factor will be read like a childhood diary, when dark energy will be as familiar as sunrise, when the expansion of space will feel as ordinary as the turning of seasons. Until then, we listen to the redshifted lullaby. We trace the ripples in the ancient light. We measure the hush that stretches the cosmos, and in the stretching find both our smallness and our belonging. For though the universe has no center, it has, in every drifting galaxy, a vantage from which the whole story can be seen, if only for a fleeting instant of cosmic breath. Imagine you could hold the fabric of reality between your fingers. It would feel like nothing. No texture, no grain, only the soft illusion of continuity. Yet beneath this quiet surface, nature hides a roar. Einstein once pictured spacetime as a flawless sheet of rubber, bent by planets, rippled by stars. It stretches, it breathes, it answers to mass and motion with perfect obedience. But quantum physics whispers a different story. It says the sheet is stitched from restless threads, twitching even when no one is looking. At every instant, in every direction, emptiness itself is alive. To meet this hidden life, we must travel inward, far inward, until the world of tables and trees and even atoms has fallen away. A proton is a cathedral compared with where we are going. Keep shrinking past electron clouds, past quarks, until distance itself becomes a ghost. At 1/10,000,000th of a trillionth of a trillionth of a meter, we reach the Planck length. Here, space and time lose their passports. Geometry forgets its lines. Cause and effect start stammering. If you could wear a watch sensitive to these depths, its second hand would twitch 10,000,000 trillion times every heartbeat. That is Planck time, so brief that the instant itself trembles. In such a place, certainty dissolves. The vacuum is no longer empty. It teems with possibilities, particles blinking into borrowed existence, annihilating before the universe notices the debt. These are the quantum fluctuations of spacetime. They are not happening inside space. They are space, jittering like a sea in a storm, forever too small for our instruments, too loud for our equations. The clash is stark. General relativity commands smooth curves, quantum theory demands dice. Put the two together and the dice fall through the curves, erasing both. We are left holding broken chalk and a board scrawled with contradictions. Consider energy. Quantum fields predict that the vacuum carries density, an ocean of latent power. Add it up over every wiggle allowed down to the Planck scale, and the total should bend the universe so fiercely that galaxies could never have formed. Yet the night sky is quiet. The measured expansion of space is gentle, almost sleepy. The discrepancy is not minor. Predictions overshoot observations by 100 trillion times. It is the most embarrassing factor in physics. Somewhere, the music between mathematics and reality has slipped out of tune. Because of this mismatch, physicists suspect our picture of spacetime is still a sketch. They search for a master equation that sings both the lullaby of large distances and the percussion of the small. Many paths climb toward that summit. Loop quantum gravity proposes that the cosmos is woven from finite loops of gravitational field. At the Planck scale, area and volume come in discrete parcels, like Morse code tapped on an iron drum. Space is no longer a stage. It is the players themselves, braided into networks whose links birth what we call distance and duration. String theory offers a softer vision. It replaces point particles with tiny vibrating strings, each note a particle, each harmony a force. To fit gravity among the chords, the mathematics asks for more spatial dimensions curled so tightly that light itself finds no room to wave. Within these hidden corridors, the graviton, the carrier of curvature, may echo, leaking into our four-dimensional world as the gentlest of whispers. Causal set theory imagines spacetime as a bag of discrete events, sprinkled like sand across a darkened beach. Only some grains touch, and from their pattern, continuity emerges as an average, the way a photograph dissolves into dots when viewed too closely. Time gains an arrow because the network refuses to loop back on itself without leaving scars. Other minds pursue emergent gravity, where spacetime is not fundamental but stitched from quantum information, the way temperature arises from the dance of atoms. Entropy, once the measure of disorder, becomes the architect of geometry. The deeper the information hidden in a region, the stronger the gravitational pull its surface can exert. In this view, curvature is a byproduct of ignorance rather than a primitive reality. Each approach carries shadows. Loop networks struggle to reproduce the elastic ripples Einstein predicted. Strings have yet to predict a single unique universe. Causal sets must explain why the large cosmos looks so flawlessly smooth. Emergent schemes wrestle with the flow of time. Still, the question keeps us awake: which story, if any, belongs to the world? To sharpen the inquiry, we turn to black holes. They are the natural intersection where gravity and quantum uncertainty must negotiate a treaty. A star collapses until nothing, not even light, can outrun its own memory. According to relativity, the core is crushed to a point of infinite density, an end of time. Quantum mechanics refuses such finality. Information, it insists, cannot be erased. Every quantum event is a palimpsest. Somewhere its history must survive. So we face a paradox. Drop an encyclopedia into a black hole. From outside, the volume of the hole increases, its surface area stretching like a balloon. Decades later, the black hole radiates a faint glow, hawking radiation, draining mass, dimming to nothing. If the encyclopedia truly vanished, the information it carried would have died with it, violating quantum law. If it survives, where is it written as the black hole evaporates? Some argue the data is encoded on the event horizon, the shimmering boundary of no return. There, every falling letter might leave a holographic imprint, smeared across the two-dimensional surface like ink on glass. When the radiation flees, it carries that smear away piecemeal, until the library is scattered in the wind yet technically intact. Others believe the information is preserved in subtle correlations within the radiation itself, a code so delicate that reconstructing it would be like reassembling a shattered teacup from steam. A bolder idea suggests the black hole does not end in a point, but in a Planck-scale nugget, a remnant that hoards the last quantum digits, defying complete evaporation. Such remnants would glow with the memory of everything they ever swallowed, tiny archives adrift in the dark. Yet no telescope has reported their twinkle. Perhaps the mistake is deeper. Perhaps spacetime around the hole is itself a weave of quantum links, and information never truly falls in. Instead, it lingers at the edge, its fate entangled with the outgoing light. In that case, the interior we imagine may be an illusion, a convenient story told by observers who remain outside. Step across the horizon and the tale changes. Space and time swap roles, and the notion of where becomes as slippery as when. These riddles are not academic. They decide whether physics ends in prediction or surrender. They decide if the universe keeps its diary in a language we can someday read. We stand on a shoreline, toes curled into grains that look continuous from afar yet separate when held to the eye. Beyond the last breaking wave lies an ocean whose depth is measured not in kilometers but in inverse uncertainty. We have maps drawn by Newton, by Einstein, by Bohr, but none shows the reefs where certainty founders. Still, the horizon glows. Each thought experiment, each equation, each satellite measurement is a lantern we set adrift. Some extinguish in the swell. Some drift back bearing fragments of an answer, a limit here, a symmetry there. Together they sketch the outline of something vast, a grammar older than light. The night invites patience. Reality does not yield to force. It yields to those who listen long enough to hear the silence between fluctuations. One day, perhaps, the lullaby of relativity and the percussion of quanta will converge into a single melody, and we will understand why emptiness is heavy, why time keeps faith with space, why information, like energy, can neither be created nor destroyed. Until then, the puzzle remains open, a cathedral under construction whose blueprints are written in starlight and uncertainty. We walk its aisles with cautious reverence, aware that every step redraws the floor beneath us, aware that the only map we truly possess is the one we draw together, line by careful line, as we follow the music deeper into the dark. Imagine, for a moment, that spacetime is not the rigid stage we walk upon but a supple fabric that can fold until distant corners touch. If you could step through that fold, you might emerge, without crossing the space in between, on the far side of the galaxy, or in the deep past, or both. Such folding is the quiet promise hidden inside Einstein's equations. Bridges, tunnels, short circuits in reality itself. We call them wormholes. The first whisper of this possibility arrived in 1935 when Einstein and his assistant Nathan Rosen tried to describe a particle as a pinched tube of spacetime. Their mathematics produced not a particle but a pair of black holes joined at the heart, an Einstein-Rosen bridge. It was elegant, symmetrical, and useless for travel. The throat narrowed to a hair's breadth and snapped shut faster than light could cross. A doorway that opens and seals itself in the same instant is, for living creatures, no doorway at all. Yet the idea refused to die. 4 decades later, a spark arrived from the blackboard of Kip Thorne. He asked not whether nature allowed such bridges, but whether an advanced civilization could keep one open long enough for a pulse of light, perhaps even a spacecraft, to pass. The answer required a strange form of scaffolding, matter whose gravity repels rather than attracts, matter with negative energy density, negative pressure. We call it exotic matter. In everyday life, energy is always positive. Even the faint vacuum energy of empty space is a positive quantity. Negative energy is like a bank account whose balance drops below zero without borrowing from anywhere. It flips the familiar energy conditions that normally keep spacetime orderly and predictable. Without those conditions, causality itself becomes negotiable. To understand why, picture a wormhole mouth left on Earth and its twin carried aboard a starship that accelerates close to light speed, then turns and returns. Relativity teaches us that the traveling mouth ages less. When it lands, the two mouths no longer share the same moment. Step through one and you might exit before you entered, creating a loop in time. Such a loop is not merely a curiosity. It permits the grandfather paradox, the billiard ball that knocks its earlier self off course, the radio signal that instructs its own transmission. The universe, confronted with these contradictions, does not scream. It murmurs a question we cannot yet answer. Does some undiscovered law forbid the loops from forming? Does quantum uncertainty smear the paradox into harmlessness? Or does the cosmos allow them, but only in tightly regulated ways, like a river that permits eddies yet never lets the water flow uphill forever? The traversable wormhole has a shopping list of demands. First, the throat must be wide, at least meters across, so that tidal forces do not shred an atom into ribbons. Second, exotic matter must thread the throat like a continuous, weightless scaffold, holding it open. Calculations show that for a human-sized tunnel, the required negative mass is roughly -1 Jupiter. That is not a typo. We need the gravitational equivalent of a planet, but with its sign flipped. Third, the interior must be stabilized against a swarm of instabilities. Tiny perturbations that grow, resonate, and collapse the tunnel before any traveler slips through. Quantum effects, which Einstein's equations ignore, stir the vacuum into froth at the very threshold. Radiation may pile up, reflecting between the mouths until the energy density rivals that inside a star. If so, the wormhole ignites in a flash of self-destruction, leaving only a scar of curved space and a cautionary tale. Even if we could summon the negative energy, nature seems to guard causality jealously. Stephen Hawking proposed the chronology protection conjecture. Quantum fluctuations might build an infinite density of light rays at the moment a time machine is about to form, destroying it. The mechanism is subtle, not a wall but a tide rising faster than any technology could bail. Other voices suggest loopholes. Perhaps closed time-like curves are allowed, yet only in regions where quantum mechanics forbids information to settle into a paradox. The future would be consistent because probability itself conspires against self-contradiction, nudging every bullet so it misses its past shooter by the width of a photon. Meanwhile, laboratories on Earth toy with the faint shadows of exoticity. The Casimir effect squeezes vacuum between two mirrors, pushing them together and proving that negative energy densities can exist. albeit on scales smaller than the width of a blood cell. Expand such a sliver to planetary size and the energy budget dwarfs the output of a star. We are like children who have found a single brick and dream of building a cathedral, yet the brick is real. It tells us the laws do not forbid the material outright, only its abundance. Where does this leave the wanderer who longs for yesterday? Wormholes remain what they have always been, exact solutions to an incomplete set of equations. General relativity allows them, quantum mechanics bristles, and the two theories refuse to share the same room. Until we possess a quantum theory of gravity, the verdict stays suspended, a coin balanced on edge, spinning in the vacuum between event horizons. Still, the mere possibility reshapes our sense of what time is. If the past can be visited, it does not pass. It lingers, fixed, like terrain seen from an alpine ridge. The future, too, would already exist, a country awaiting footsteps. Our lives would be less like a story told once and more like a canyon etched by countless crossings. Each decision would echo along the loop, returning to us like wind wearing the stone. Perhaps that is why the sky is silent. Civilizations that mastered wormholes might have stepped outside history, leaving the universe to its quiet expansion. Or perhaps the doorway is never wide enough, and every species meets the same ledger of impossible demands. We are left with questions that gleam like frost in starlight. Does the universe permit shortcuts, or does it unfold the long way round, every mile paid in full by light and time? We do not know. We walk the long way, carrying the equations like lanterns, watching the frost gather on the handle, feeling the hush that follows every unfinished sentence. Imagine for a moment that the universe is not silent, that every turn of a planet, every spiral of two black holes, every flicker of a supernova is accompanied by a faint tremor in the very fabric that holds us. Not sound as we know it, there is no air in space to carry the vibrations of voice or violin, but a quiet shiver of distance itself. A momentary shrinking, then stretching, of the space between two hearts, between two stars. Einstein predicted this hush in 1916 on the heels of his greatest epiphany. If mass can bend spacetime into curves we feel as gravity, he reasoned, then surely a restless mass, one that jerks or spins or collides, must ruffle the entire sheet. The disturbance would flee outward at the speed of light, a ripple of geometry rather than of matter, carrying away news of violence elsewhere in the cosmos. He called them gravitational waves, and for nearly a century they remained a beautiful idea with no passport stamp from reality. We should pause here at the edge of possibility to picture how delicate such a wave truly is. A pair of neutron stars, each the mass of our sun yet squeezed into a city, whirl around one another 100 times per second. Their dance distorts spacetime so powerfully that, out in the galactic suburbs where Earth drifts, the distance between two unassuming points changes. Not by the width of a hair, not by the width of an atom, by far less. 1,000th the charge diameter of a proton. To detect that shift across the 4 kilometers of a laboratory tunnel is like gauging the addition of a single grain of sand to all the beaches of the world. It sounds impossible, but impossibility has never stopped the patient. So we built L-shaped vacuum tunnels in the pine forests of Louisiana and the wheat fields of Washington state, then later in the olive groves of Tuscany. Inside, laser beams travel back and forth along polished mirrors, counting the light seconds like a metronome. When a gravitational wave passes, one arm shortens while the other lengthens, and the crest of the laser wave arrives a little earlier in one detector, a little later in the other. The signal is a wobble smaller than the jitter of the mirrors themselves, smaller than the rumble of distant traffic, the hiss of ocean surf, the seismic sigh of continents drifting. To pull truth from such noise, physicists learn to listen in triplicate. 3 interferometers, separated by continents, must all murmur the same strange song before anyone believes it is the universe speaking. On the 14th of September, 2015, at just past 9 in the morning GMT, the first tremor arrived. It had traveled for 1.3 billion years, born when multicellular life on Earth was only a hopeful experiment. Two black holes, 36 and 29 times the mass of the Sun, had collided in a galaxy so distant that its light has not yet reached us. In the final second before they merged, they shed more energy than all the stars in the observable universe combined. 3 suns worth of mass converted entirely into pure ripples of curvature. The detectors caught that crescendo, a faint rising whoop inside the data, then fell silent again. The sound, if we may call it that, lasted barely a fifth of a second. Yet in that whisper lay the vindication of a century's patience and the birth of an entirely new astronomy. Since that first note, dozens more have followed. Black holes of 50 solar masses, of 90, of 140, spinning like tops and sending out tremors we now recognize as easily as birders know thrush from wren. Then in 2017, a new timbre, the clash of neutron stars, dense enough to squeeze Mount Everest into a teaspoon. Unlike black holes, these remnants carry luminous baggage, gold and platinum forged in their fiery embrace. So telescopes, from gamma-ray eyes in orbit to humble light gatherers on mountain tops, saw the same event. For the first time, a cosmic courier arrived in 2 envelopes at once, one written in electromagnetic ink, the other in pure geometry. We learned that colliding neutron stars are the universe's crucibles for heavy elements, that the wedding ring on a human finger was once forged in the death spiral of anonymous suns. Each detection is a postcard, and the message is always distance. Gravitational waves arrive unblemished by dust or magnetic detours. They travel through the very steel of stars untouched. They carry the polarization of the wave, patterns of squeeze and stretch that betray whether the ripples slosh side to side or spiral like the threads of a screw. From such tilting, we have begun to map the sky by ear alone, sketching populations of invisible black holes too dark for ordinary telescopes. We have measured the expansion rate of the cosmos, the Hubble constant, without needing to calibrate candle stars or cosmic mileposts. The answers still carry uncertainty, but they are independent, a second ruler against the same vast wall. And what of energy? A wave is not merely a wrinkle, it is a courier of vitality across the void. When the sun's light warms your cheek, you feel the transport of electromagnetic energy. Similarly, gravitational waves ferry away the orbital life of a pair of bodies, sapping their motion so that they inch ever closer, ever faster, until the final embrace. Einstein's equations insist that this leakage is inevitable. Without it, the dance would cycle forever, a perpetual motion machine forbidden by nature's fine print. In the end, the waves are the universe's way of enforcing a balance sheet. Pay the toll of radiated curvature or relinquish your place in the cosmic ballet. We stand now at the threshold of an auditory renaissance. Plans are drawn for detectors 10 times more sensitive, able to hear black hole whispers from the adolescent cosmos, when the first stars were only beginning to ignite. We hope to sense the drone of countless small waves, a stochastic murmur like radio static, possibly left over from the first instant of inflation itself. Perhaps we will hear the drumbeat of a lone neutron star cracking under magnetic stress, or the sigh of a white dwarf being slowly devoured. Each new frequency band is a new color in an expanding palette. By mid-century, humanity may listen to the sky with the same casual richness with which we now glance upward and see blue. Yet mysteries remain. We have not detected waves from supernovae, though theory says they should scream. We do not know whether small black holes exist in the void between galaxies, nomads of darkness. We cannot yet pick out the gentle lapping of a planet mass wave, the hush of a moon falling quietly inward. And threading through these uncertainties is the deeper riddle. Why does spacetime, alone among fields, remain faithful to the classical stage while the rest of creation bows to quantum law? A fully quantized gravity may one day predict a graininess to the ripples, a foam that subtly blurs their crests. Until then, every detection is a reminder of how much we still do not grasp. Still, there is comfort in knowing that the cosmos is not a silent museum. It is alive with tremors, a quiet ocean on which we drift in a small wooden boat, occasionally feeling the gentle lift of a passing swell. We are learning to read that motion, to know whether it comes from a distant storm or from something stranger still. In doing so, we are reminded that distance is not emptiness, and that nothing in the universe is ever truly still. Even now, as you listen, the space between your hands is breathing, an exhalation so subtle that only the patient mirrors of an interferometer could ever testify to it. And so, we will keep listening. For every silence we shatter, another replaces it, deeper and more inviting. Out there, perhaps, two black holes are already winding toward each other, their final kiss sending a tremor that will reach Earth long after our cities have turned to stories. When it arrives, may someone be waiting, ears tuned to the curvature of space, heart open to the knowledge that we are forever held by the same fabric we disturb. Until that moment, let the ripples pass through us unimpeded, a gentle reminder that even the quietest motions can carry the weight of galaxies. The music is not over. After centuries of measuring, calculating, and listening to the cosmic score, we can finally hear the first clear notes. Planets wheeling, light bending, black holes chiming like low drums in the dark. Yet whole movements remain missing. Where the orchestra should swell, we meet a hush, an expectancy that refuses to resolve. One absent voice is loudest in its silence: dark matter, a name we gave to our confusion. We see galaxies spinning so fast they should fling their stars into the void, but they do not. Something 5 times more plentiful than ordinary matter holds them together, yet it never shines, never touches, never collides. It slips through the spaces between your fingers, between planets, between heartbeats. All we know is the echo of its gravity, like noticing a hidden stream only by the trembling of reeds on the surface. Earthly detectors rest deep underground, waiting for a single nudge that would whisper, "Here I am." The patience is monumental. Years pass like seconds in the cold silence. If we are honest, we still cannot say whether dark matter is a fog of unseen particles, a swarm of primordial black holes, or a misunderstanding of the score itself. An error in how we read the curvature of spacetime on the grandest scales. Even more mysterious is the dark energy threading the emptiness. Where matter thins to nothing, this pressure remains, pushing. Every cubic meter of space contains a few atoms of hydrogen and a sliver of a joule of this strange vitality. It is so dilute you could never feel it here, yet across billions of light years it outshouts all other players, accelerating the expansion of the universe. Imagine a loaf of raisin bread rising so fast the crust itself is torn. We bake equations to describe the swelling, but we do not know what the yeast is. Quantum physics predicts a seething froth of virtual particles, furnishing an energy to empty space, yet the amount it offers is 10 to the power of 120 times larger than what astronomers measure. Calling that disagreement awkward is like calling the Pacific damp. Some physicists wonder if dark energy is a constant, a relentless note forever held. Others suggest it may change, a crescendo that could end in a ripping finale. Until we measure the expansion with finer brushes across the eons, the answer sits just beyond the edge of the observable sky. These two shadows, dark matter, dark energy, share a secret. They are landmarks in our ignorance, not in our knowledge. They remind us that spacetime, the the flexible stage on which every star performs, might conceal hidden dimensions, new fields, or forces that touch ordinary matter only through the subtlest of whispers. Perhaps one day a schoolchild will write an equation half a line long that folds these ghosts into the fold of light and mass, and the account will seem obvious in retrospect. Until then, we watch galaxies collide, chart the afterglow of the Big Bang, and count supernovae as if counting heartbeats in a sleeping giant. Yet there is another fracture in the symphony, deeper, more conceptual. General relativity speaks the language of continuous curves. Quantum mechanics speaks the language of grains and jumps. When both try to describe the same moment, say, the heart of a black hole or the instant of the Big Bang, their vocabularies clash like discordant chords. We need a single tongue, a quantum gravity, but the dictionaries refuse to merge. In loop quantum gravity, space itself is woven from threads of area and volume, each loop 1 Planck length across, a distance so small that comparing it to a proton is like comparing a proton to the Milky Way. In this view, the cloth of spacetime is a tapestry of knots, and what we call smooth geometry is only the coarse weave seen from afar. String theory offers a different palette. Tiny vibrating strings whose harmonics give us electrons, quarks, photons, and, yes, gravitons, carriers of gravity. To make the maths blossom, strings demand extra dimensions curled so tightly we stroll through them unawares, like ants crossing a hosepipe lying hidden in long grass. Both avenues are beautiful, both incomplete. Neither has yet told us why the universe chose the constants it did, or what happens when a particle meets its own reflection traveling backward in time. The clash becomes acute at singularities, places where curvature grows infinite and time itself stalls. Inside a black hole, relativity predicts a point of zero volume and infinite density, a cosmic punctuation mark where the story ends. Quantum physics abhors infinities, it smears certainties into probabilities. To pierce this veil, some researchers follow the collapse in computer simulations, watching matter squeeze until quantum repulsion stiffens against the plunge. They glimpse a bounce, a hidden gateway, a possible birth of a new region of spacetime on the far side. Others hunt for traces in the sky, patterns in the microwave background that might record the bruise of a primordial singularity. The data remain frustratingly bland, the universe refusing to reveal its scars. Until we can coax a quantum theory of gravity into making a clear, testable prediction, singularities remain lighthouses beyond the shore, warning of reefs we cannot yet map. Testing gravity where it is strongest has become the frontier. Close to a black hole, orbital speeds approach the speed of light, and spacetime curvature tightens until Newton's portrait of gravity looks like a child's crayon sketch. Stars whip around Sagittarius A*, the 4 million solar mass giant in our galactic center, completing orbits in mere years. Their tracks trace a shallow funnel in spacetime, letting astronomers measure the drag of the hole's spin, a quantity that encodes the entire history of its growth. Laser interferometers on Earth listen for the faint tremor when two black holes merge a billion light-years away. Each ripple washes through the arms of the detector, shifting the length of a 4-kilometer vacuum tube by 1,000th of a proton's width. From that whisper we reconstruct the masses, spins, even the love affair of horizons spiraling into one another. Soon, space-based antennas will open ears tuned to lower frequencies, where supermassive black holes circle in a slow waltz, their song carrying memories of galaxies knitting together in the adolescent universe. Future voyages will carry atomic clocks so precise that climbing 1 meter higher in Earth's gravity shifts their tick. By comparing orbiting clocks with those on the ground, we will chart the planet's gravitational field as delicately as a physician mapping a heartbeat. Probes will skim closer to the sun, watching starlight graze its roiling surface, testing whether the deflection still matches Einstein's prediction to the 10th decimal place. Deviations, even a whisper, would herald new particles or new dimensions curling in the heat. Elsewhere, radio dishes will synchronize across continents, forming an Earth-sized telescope sharp enough to image the shadow of the black hole in the galaxy's core. Already we have seen the dark outline against the glowing gas, a circular absence framed by light bent full circle. Sharper images will reveal whether the shadow is perfectly round, as general relativity demands, or slightly squashed, hinting at a hidden spin coupling to some undiscovered field. All these instruments share a quiet ambition: to catch spacetime misbehaving. Perhaps the speed of light is not quite constant for all frequencies, or gravitational attraction weakens by a hair at distances smaller than a hair. Such slips would not be failures. They would be entries in a traveler's journal, telling us the continent of physics continues beyond the edge of our maps. Science advances not by the confirmation of what we know, but by the surprise of what we never thought to ask. Still, the largest questions drift beyond experiment into the realm where philosophy and physics share the same breath. Why does spacetime exist at all? If it emerged from a quantum fluctuation, what trembled? If time began with the Big Bang, what does before mean? Does the universe have a purpose, or is purpose a mirage seen by patterns of carbon that have learnt to wonder? We stand on a small wet world, our lives the thickness of a single stroke in a vast fresco, yet in those minds the universe contemplates itself. The unfinished symphony is not a flaw, it is an invitation. Each generation inherits the score, adds a phrase, passes the baton. Somewhere, in a laboratory not yet built, a student will align two mirrors and notice a fringe shift no model predicted. In that instant, the fog will lift and a new movement will begin. Until then, we listen, we measure, we dream. The night is quiet, the stars are steady, and the music we cannot yet hear is already on its way. The night sky looks quiet. Stand on any hillside, far from city glare, and the stars appear pinned to velvet, silent and eternal. We have gazed upward this way since before words, before farms, before fire. And yet every one of those still points is sliding through a dark medium we can neither see nor feel. A scaffolding so supple that it quivers when two black holes collide a billion light-years away. We call the medium spacetime, but the name is only a suitcase for a concept our senses did not evolve to unpack. Consider the moment you first noticed, as a child, that your reflection in a spoon was upside down. The distortion was amusing because it defied expectation. The metal simply did what metal must, and your eyes had to catch up. Einstein's universe demands a similar recalibration. Only the spoon is the cosmos itself, and the image is you. We grow up believing that intervals are rigid and clocks impartial, that 1 second here equals 1 second on the rim of a distant galaxy. Relativity quietly informs us otherwise, and the quietness is the trick. The changes are too small at human speed to bruise our intuition, so we cruise through life assuming the mirror is flat. But mount two synchronized atomic clocks, one on the ground, one on a jet. When the plane lands, the traveling clock has aged less by billionths of a second. The difference is real enough to reset navigation satellites every day. Without the correction, your phone would misplace your street corner by kilometers. Thus, even our most mundane requests for directions already rely on the elasticity of time. We live inside the contradiction. A species that can split atoms while barely perceiving why noon arrives sooner at sea level than on a mountaintop. What does it mean to occupy a mutable cosmos? Imagine a vast lake frozen over. You skate from shore to shore, tracing a straight line, and you swear the geometry is Euclidean. Below, the water stirs with currents you cannot sense. Spring arrives, ice thins, and the same journey must detour around soft spots. The surface you trusted was never the whole story. It was a temporary concession among temperature and pressure. Spacetime is that lake, except the ice and the water are the same substance, and spring is any concentration of mass. The sun, a modest star, dimples the sheet so thoroughly that Earth's path becomes a circle by consent, not by contact. We are skaters who never notice the bending because we ourselves are made of ripples. This realization lands lightly at first, then settles like snow on skin, cold and undeniable. Our bodies are event collections, temporary gatherings of carbon and water riding a slice of now that sweeps forward at the speed of light. The past is not a place behind us. It is the set of all light cones that have already folded back onto the night. The future is not ahead. It is the region of spacetime we have not yet intersected. Language strains to deliver the news without sounding like mysticism, yet the physics is stricter than any incantation. Still, we are equipped with only 3 layers of perception. Photons tickle retinas built from ancestral ocean cells. Pressure waves bend hair cells in a cochlear spiral. Chemical keys fit protein locks on tongues and in noses. From this modest toolkit we extrapolate galaxies. The miracle is not that we sometimes get it wrong. The miracle is that we get anything right. Our brains evolved to throw stones and read faces, not to visualize 4-dimensional manifolds. So we build stories, metaphors, instruments. A radio dish in a desert meadow becomes an extra ear, hearing the slow murmur of hydrogen memories when the universe was 1/10 its present size. A laser beam, split and folded into an L-shaped tunnel, can sense a distortion 1,000 times smaller than a proton, a ripple born when 2 stars collapsed into darkness before our solar system existed. Each extension is a borrowed sense, a prosthetic wonder that allows flesh to reach beyond its contract. Yet even the augmented map bears blank parchment. We see 5% of the cosmic budget, the luminous trifle of atoms that glow or block light. The rest is a ghostly majority we have named dark matter and dark energy, placeholders for gravitational habits we cannot otherwise explain. Perhaps these names will sound as quaint as phlogiston once we learn to see them. Perhaps they will dissolve into a deeper geometry, the way temperature dissolved into the jostling of unseen molecules. For now, they remind us that every epoch believes itself on the verge of completion, only to be nudged awake by the next anomaly. Einstein himself never shed the suspicion that the universe should be simple enough to fit behind the eyes. Late in life, he wrote of a cosmic religious feeling, a phrase that annoyed both the faithful and the skeptics. He did not mean a deity who counts sins. He meant the awe that arrives when reason finds itself pressed against the inexhaustible. The emotion is not proprietary to physicists. Anyone who has held a newborn and then looked at the Milky Way feels the same vertigo. The span from heartbeat to galaxy is 10 orders of magnitude, yet both are places where hydrogen has learned to wonder about itself. This kinship between the microscopic and the astronomical is not poetic excess, it is structural. The calcium in your bones was forged in a star that refused to settle for hydrogen, that reheated its core until the nuclei bloomed into heavier currency. The iron coloring your blood was the ash of a supernova that lit up the neighborhood before Earth had a neighborhood. When you press your finger to your pulse, you are listening to a drum stitched together by extinct suns. Spacetime is the fabric, but the embroidery is borrowed starlight. Still, the mind keeps circling back to limits. We cannot remember being born, we will not witness being dead. The interval between is our only observatory. From this narrow slit we peer outward, building telescopes that float above atmospheric glare, arrays that stitch continents into single eyes. Each generation inherits a sharper picture, and each sharper picture reveals new shadows. The universe seems almost playful in the way it keeps its secrets just around the corner, close enough to tease, far enough to require another lifetime. Imagination is the counterbalance. It is not the idle spinning of fantasies, but the disciplined art of asking better questions. When Einstein asked what it would feel like to ride beside a light beam, he was not daydreaming. He was holding the contradictions of Maxwell and Newton in the same mental hand until they fused into something new. The thought experiment is our most portable laboratory. No grant proposal, no heavy lift rocket, just the willingness to sit still and refuse to let yesterday's definitions govern today's perplexities. In that sense, every child who wonders why shadows lengthen at sunset is practicing the same craft as the physicist who calculates gravitational lensing. The difference is only in the patience to follow the thread past bedtime. The continuing quest for deeper understanding has no finish line. Each answer begets a finer question, like a Russian doll that refuses to end in the direction of the small. We may yet discover that spacetime itself is a coarse weave of something more intricate, the way sand appears continuous until you meet its grains. Or we may find that the notion of granularity is itself a projection of limited senses. Either outcome will redraw the boundary between what we call substance and what we call void. The only certainty is that the universe will remain stranger than we can currently articulate, while remaining lawful enough to allow articulation to improve. Einstein's influence persists not because he delivered final truth, but because he demonstrated that humility and audacity can share the same skull. He could overturn space and time without ever losing the courtesy to wonder what it felt like to be a beam of light. In an age when certainty is marketed like breakfast cereal, his legacy is a quiet insistence that the most important discoveries begin with an admission. I do not yet understand. The sentence sounds like weakness. It is the hinge on which every lever of knowledge turns. So we stand beneath the same stars our ancestors used to navigate cattle paths across deserts. The patterns have shifted slightly over millennia, but not enough for the naked eye to notice. What has shifted is the story we tell about what cannot be seen. Once, the night was a dome perforated by campfires of the gods. Then it became a clockwork of crystal spheres. Now it is a stretching ocean in which every glance into the distance is a glance into the past. Tomorrow it may be something even stranger, a realm where time emerges like temperature, where space is woven from entanglement, where the distinction between here and there dissolves into correlations that do not fade with distance. Whatever shape the story takes, we will still be the species who first noticed that noticing itself alters the world. To measure is to disturb, to observe is to participate, to exist is to bend the very fabric that carries us. The realization does not belittle us, it enlarges the cabin we occupy. We are not passive passengers on a cosmic train. We are crew, our collective choices about curiosity or indifference steering the only vessel guaranteed to feel wonder. The night sky looks quiet, but listen longer. Beneath the hush, spacetime stretches like a drumhead, waiting for the next collision, the next thought, the next child who will ask why the stars do not fall. The question is old. The silence around it is new each time. And in that silence, in that interval between heartbeat and starlight, the conversation continues.